Welcome this morning. We are coming to you live from Santa Barbara. Let's get this show started. There we go. Let's get some screen in there. And I'm really big. Welcome. And live from Santa Barbara, this is Westmont College Mayterm CS-030. We're broadcasting from Winter Hall. And we are got a different mix of studio audience and remote folks today. So shout out to our friends in LA and Joy, wherever you're watching from. Boaz is no longer on the train. It's exciting to do this remote and dynamic. This seminar is part of a 5-week class. We are scheduled for 2 hours today, and we are communicating in real time on Slack. And if all goes well, I will pick up on any real-time comments that are there. We're on hashtag broadcast questions. And let's go. We got a lot to cover today. I'm excited. But not all of my tools are totally working right now. So there's that. Give me 1 second, and we will try and get back online. There we go. Great. All right, so let's just arrive. Make sure that our devices are turned off. Our notifications are set the way we want them to be. Make sure our folks online can see us. And just recognize why we are here. We are here to learn some skills, hopefully put them to better use to build the kingdom of God ultimately. And we want to recognize that. As we've been starting our class, we have been thinking a little bit about regulation. We've been building on that. It started with this idea of legal regulations, and we introduced the idea of social norms. These are two different ways in which our behavior is regulated. And as computer scientists, we often find ourselves in positions where we're butting up against those regulations, legal regulations, because they are trailing behind some of the some of the capabilities of technology enable us to do things or see things or accomplish things that legal regulations haven't quite caught up with and help to set some boundaries of what's important, what's ethical. We have social norms that do that as well. These are things we talked about, the ways in which we might use smartphones and the ways in which it's not okay to just use someone else's smartphone without asking them. That's a social norm. It's not a legal regulation per se, but it's something that, like many things, our behavior is regulated by social norms. Well, another thing that regulates our behavior is economics or market forces. These aren't legal regulations, and these aren't exactly social norms. I guess you could talk about them as social norms in some sort of broad way, but I think they're a different kind of social norm. And it's the fact that what we do is dictated a lot of times by what the cost of that behavior is. Again, a little bit different than the previous two, but we might throw this out there. How do you change your behavior based on the cost of your data plan? A lot. What do you do? What don't you do?
Well, I used to not have unlimited data.
Okay.
And now I do have unlimited data. And when I didn't have it, you're almost always kind of thinking about is this using data? How much data do I have left in the month? Can I actually be doing this right now? And now it's just I can do whatever I want from my phone, and it doesn't matter as much.
So you shifted from not having unlimited, thinking about data all the time, and then shifted to unlimited, and suddenly you didn't have to concern yourself so much. Did you find yourself moving around to try and find Wi-Fi locations in order to do stuff for free?
Sometimes, yeah. Sometimes it would be I wouldn't go to the park to do my homework. I would go to the library.
Yeah. And I think a lot of times people will do stuff like, if you are paying per bit on your data plan, you won't watch videos when you're out. Right? You might use it to pay for directions or something, but you're going to hold off on Skyping or FaceTiming through your device if that's something that you do. Well, that's behavior that's being regulated because of an economic force. I wouldn't say that falls into the category of ethical behavior necessarily, but it does change the social norms, because if you're out eating somewhere and there's not Wi-Fi, well, you're less likely to show someone a video. And so that becomes sort of a social norm along the way. And suddenly when there's unlimited data, well, the social norms start to change, because now you can show that funny video or the thing that your friend sent or something like that. And that subsequently changes our experience when we're in places that used to be sort of walled off from data. The idea of being on an airplane, now that you have Wi-Fi in the airplane, has totally changed what it's like to be on an airplane. It used to be kind of this secluded cave, and now it's like you're next to the person on the phone, and that's the phone. What about other ways in which our behaviors change? What about the cost of gas? I don't know if you guys have cars or not, Do you do things differently because of the cost of gas? Is it electric or just kind of a small car? Oh yeah, that's a great
In
observation.
California, Arizona, one person can pay for gas to drive like almost all the way across the country.
Well, so I think one thing that's at play there is that California has stricter emissions requirements, and that then gets wrapped into the chemical formulation of the gas.
Taxes on gas and all sorts of stuff. It's like
Why are the taxes on gas there?
there are way more people living here.
Yeah, but what do the taxes on gas do?
Well, it make you not want to buy it.
They regulate your behavior through an economic force, right? That's a lot of times what exactly taxes are supposed to do. They're supposed to make something more expensive to reduce the amount of time that or amount of
I have a question.
execution of that. Sure.
If you want to tax people based on something you don't want them to do, well, like a sin tax, like taxing alcohol or smoking or something like that with gas, why would you tax income? Like you don't want people to earn income.
Oh, well, not all taxes are the same or achieve the same ends, right? So you tax people who make less money less. So we have a progressive tax system because the rationale for that is that the first $50,000 you make is much more valuable to someone than the second $50,000 they make, because that first $50,000 will buy you food and water and energy, and the next 50,000 you start to buy things like fancier clothes and going out to eat. So in that way, it's not quite as, that's the rationale for progressive tax policy. You may disagree with it, but that's at least the argument for it. And so that's not about regulating behavior, right? So same thing with property tax. Property tax, income tax, property tax, and sales tax are typically the three pillars of tax policy. And then outside, that's just to fund your social programs. But outside of that, then you start to get into behavior regulation or funding different things. Like one of the reasons why there's a gas tax is to pay for roads, because the people who use the roads pay for gas. And so it makes sense that you charge the people who are using the roads to maintain the roads. You do that through a tax. So there are different ways that it works, that's for sure. But Lisa, your observation about people sharing the cost of gas when you're kind of carpooling, that's a really interesting dynamic between the economic force and then what becomes socially acceptable. Yeah, it depends, right? Social norms are a little bit more fuzzy, I think. Cost of tuition. Do anything differently because of that? Maybe.
I'd say the group of people you receive, like if this is specific with college, the group of people you're going to receive at like a more expensive college, especially modern. I don't want to mess this up, but I don't know. The groups of people that you're going to receive at differently priced colleges are going to be different because of status norms and the amount of money that groups of people have.
Yeah, so depending on the cost of a college, different people can attend. And so financial aid policy is a lot about trying to enable people who otherwise couldn't afford expensive colleges to go to expensive colleges. In fact, financial aid is like a huge economic leveling force, assuming that the colleges are providing something of value. Yeah. I see a lot of people making decisions about where to go in summer based on the cost of tuition, whether they're doing a community college course, something like that. Yeah, but it changes our behavior one way or another. All right, so thinking a little bit about that is helpful, setting us up for thinking about how code interacts with those things. So administratively, where we are right now is we've got a lot due. So we've got 2 quizzes and a programming assignment due tomorrow. So one of those could be accomplished today. You don't have to wait until the last minute to accomplish things. I'm just going to throw that out there. Chapter 6 is on loops. Chapter 15 is on the Java collection framework that we're going through today and yesterday. And the programming assignment is about using JMonkey Engine to build a pyramid. So hopefully that's fun and not super taxing. We do have an exam on Friday. And for those people who are remote, meaning not on campus, we're going to be using a service called Proctor Free. And you'll notice that on Canvas, there's an assignment that is designed to have you work with Proctor Free and make sure that your technology is in place. So mostly this is to our folks that are participating remotely. Please log on and do that Canvas assignment to make sure Proctor Free is going to work. What that means is on Friday, there'll be a 12-hour window in which you can take the timed exam using the Proctor Free service. Basically what Proctor Free does is they record you via your webcam and they record your screen interactions to make sure that you are not cheating on the exam. You'll take the exam through Canvas otherwise, but while being monitored by Proctor Free. We're trying this service out, see how it works in terms of maintaining integrity in our exam process, and we'll adjust course as necessary. Meanwhile, people locally will just do it on paper. Okay, and then we have another assignment due the following Sunday. Boaz.
Do you want us to do the setup assignment?
Yeah, I'm not going to require it. It would be great for you to do it just so that we can see how well it works. Actually taking the exam costs Westmont money, so we're not going to actually deliver the exam to people who aren't remote, but that practice thing is free. Okay. So that should be okay. You guys don't really have to worry about it, but just so you can understand why I'm asking some people to do it on paper. Okay, last time we talked about the Java Collections framework, and we looked at several of the different pieces. So I've drawn this subset of the Java Collections framework out for us in the diagram. It is a hierarchical diagram, and it shows different interfaces in white, meaning collections of methods, and then it shows different implementations in red, meaning objects that you can actually use the new keyword on in order to instantiate a certain kind of data structure. Anything that's a child of a white box has to implement all the methods that the white box says that it needs to implement, plus it can implement additional ones as well. So we talked about the collection itself, which basically has add, remove, and the ability to iterate, but doesn't say anything about the ordering or the properties that causes. We also looked at list and set. We touched on set. We're going to launch here with set in a second. And we looked at the implementations for array list and linked list. And we saw that two different implementations have different properties based on the way in which they were implemented. We did some timing of different methods in order to validate that. So what we're going to do today is try and walk through the rest of these and do some examples with them and kind of get a sense for how you might use them in different places. So as we were looking at the list last time, we saw that there were three different ways of iterating over a list. Iterating over, a list, that's right. The first one on the right, that would be a way of iterating where we actually worked with an index, an integer index. And you can see in that case what we did is we created a variable called I, and we manually managed the process of picking the indices of our list. So we started with 0, and we ended with 1 less than size. And we, in the body of the loop, we used that integer in order to index into the list by calling get and getting the number of the element we wanted. So we first got element 0, and then 1, and then 2. And in this code here, the upper box, we don't actually do anything with that element at this point. So that's one way of going through a list, and that leverages the behavior of a list that the elements in a list are ordered. So you can actually say position 0 and position 1 because that makes sense with the concept of a list. The second case is an example of an iterator, and oh, I'm sorry, the slide is cutting off the right side. That says mylist.listIterator, and it's a constructor, so you just have the parentheses at the end. And what this is doing is this is creating like a cursor that moves over the list like a cursor that might move over a sentence in a word processor. And the reason why you might use an iterator is because you want to adjust the list as you're moving up and down it. Because with an iterator, you can actually add things or subtract things and add or remove things in the middle. And we do that usually with a while loop. We'll say while there is another element, so while it's in front of a given element. And if it is in front of a given element, then we say next. And as the cursor moves over that element, we move our iterator forward and we return an element that we want to work with. And then probably the most common and easiest one is fast enumeration down there on the bottom. Anything that has an iterator, any collection that has an iterator, we can do a fast enumeration over them. And that's a lot like doing the work in the top box, but we do it just in one single line where we define an element variable that is of type string. We use that colon syntax to say, just give me a fast enumeration over the collection on the right side of the colon. And then we saw different operations have different speeds. I mentioned that previously. Linked lists have fast insertions, and array lists have fast lookups by index. All right, so we're starting with sets at the end of yesterday, and we know that sets are different than lists because they are unordered and they don't allow duplicates. And this picture of vegetables is here to demonstrate that there are a big pile of things that are different. Please ignore the fact that there are more than one potato down there at the bottom. The idea is that you have one of many things. They're put into a big, a metaphorical or conceptual basket. The ordering isn't important, just whether or not something is present is important. So there are two kinds that we can use in Java collection framework. The two kinds I want to draw your attention to: the hash set and the tree set. The hash set keeps similar elements next to each other so that when you ask whether or not one of them is present in the set, the implementation can quickly find them. So maybe you keep all your orange vegetables together or all your leafy vegetables together. And when you ask, is there a carrot, you go and you look in the area that has orange vegetables and you find them very quickly. A tree set keeps them all in order in the implementation, although the contract for the set doesn't guarantee any kind of order. But the order that it keeps them in is not the order in which they were added to the set, and it's not even a linear order. It is a tree-based data structure that we haven't really talked about yet. And in order to put things into a tree set, you have to be able to use a compare to method because they come out in an order if you want them to. Okay, so when do you use them? Well, typically you use a hash set. It's faster. It is the default choice, and unless you know that you're going to want to pull the elements out of the set in the natural ordering, you typically will use a hash set. So we're starting to look at the creation of these sets last time, and I want to give you 6 different ways in which you could possibly initialize and create a set in Java. I'll list them here for you. In the left column, you see the implementation is hash set in each row. And in the right column, you see that the implementation is tree set in each row. But the implication of what you can do with the names variable changes over each one of the rows and columns. So in the upper left, after we're done declaring the names variable and implementing it with a hash set, the only methods that we're able to call on the variable names are those associated with the collection interface. Although HashSet has some specific methods and sets themselves have specific methods, we can't use them because we'd said that names is a collection type. Nonetheless, we can implement a collection with anything that falls under it in that hierarchy, HashSet being one of them. On the contrast, on the right, we also have only collection methods being used, but we're actually implementing it with a tree set. So after we run, if we were to run the code on the left or the right in the top row, after we run that code, we would be able to do the exact same thing with our names variable, only those methods associated with the collection interface, although the actual implementation is lost as we move down in the code because we only know that names supports collections. Now, in the second case, we get a little bit more specific. We say names is now a set type. And since it's a set type, we now can use all of the methods that are associated with a set in addition to those that are associated with a collection. And we end up implementing it with a tree set, but we can't use any of the methods associated with tree set because we declared names to be of type set. Same thing on the left, except that we are declaring it as a hash set, or we're implementing it with a hash set and declaring it to be just a generic set. So again, in the second row, after we're done with the second row, whether we did it with the left side or the right side, we're going to be able to do the same methods with the names variable because we declared them both to be of the same type, even though that we're implementing them differently. In the third row, we're choosing to declare that names is of type hash set. And so we also therefore have to implement it with a hash set. We couldn't implement it with something higher in the hierarchy. It has to be more specific. And at the end of that, we can call any methods that are specific to a hash set. And likewise on the tree set, we can call methods with collection set or tree set. So those 6 ways all are valid ways of creating a new collection, second, new set, and third, a new specific kind of set. What you're allowed to do with that variable in the following code varies, and that dictates what it is you want to do with that variable, dictates what your choices are in terms of declaration and implementation. All right, so what I'd like to do is I'd like to try this out with you guys, and we want to ask several questions. If we make a set, and we add something to the set, we know that's a method that's associated with the collection class, add. What happens to sets if we add duplicates? Then we want to ask, how does remove work? What happens if we remove an element that isn't present? How do iterators work? And then how does fast enumeration work? Okay. So let's kick over to Eclipse, and let's start with looking at how add works. And I think that in this case, what we'll do is I'll share the project with you. So let me fire up Saros and make sure I'm connected. I'm not. And then the project that we're going to share is going to be the Java Collection Framework. I'll give you a second to come online. And I'm just going to make a new class while we're doing that, that's going to hold the different examples that we're going to do today. I'll call it Examples Live. Finish that up. All right, so what we said we're interested in is we said we're interested in creating a set. Let me bring the folks that are available online. Great. When other people come online, we'll share with you guys. And Tim. And I'm going to leave it so you guys can edit it, but hold off on editing for a second. All right, so the question was, what do we do if we have a set and we add something to it? All right, so first thing we need to do is we need to declare a set. And so I'm going to use the set interface in order to define my type. So it's going to be a set, and it's going to contain, what do you want to contain? What do you want to put in our set today? Strings, most fun. Okay. And we'll call it, what are we going to keep track of in our set? Names. Good. All right. Names of, we did royal family yesterday. Let's do, what's that? Administrators at Westmont. That's fun. Okay, so we have a variable. That's enough to declare a variable. We need to import the set class, and so this is a Java util set. Did that. We have declared the variable. We haven't, so right now it's null. So names is going to point equal to null. Well, not technically. We would have to actually say it's equal to null before we did anything with it. Now it points equal to null. We actually want a set to work with, though. So immediately after line 9, we're going to assign it a new set. What kind of implementation should we use? We don't really know what we're going to do with it. And so in absence of any other idea, we should use a hash set, because hash sets are faster, except in the situation where we want the keys out in order. All right, so new hash set string. Need to import my hash set. There we go. So we are creating a new hash set. The parentheses at the end mean we're calling a constructor. And what's going to be in the hash set are strings, and that has to match what we said names is going to contain, which is strings as well. All right, so let's add some names. Who's our favorite administrator this morning? Dr. Patterson. You don't feel like an administrator, but that's okay. And then let's add Dr. Beebe. And one more. Dr. What is it? Dr. Okay. The psychology professor, Dr. C. Okay. Yeah. Dr. C. He's in my cohort. All right, so we have added 3 things to a set using the collections framework. And so what we've done here is really no different than what we would do with a list or a linked list or an array list. But maybe what happens as a result ends up being a little bit different. So let's do fast enumeration and go over the different elements in names. Let's just print out what it is that is in our collection now. All right. So we run that. That did not prove my point at all. Let's try that. I reordered them. Great. Okay. So I wanted to make a point here, and the point was what? Well, the order doesn't stay the same. Yeah. But the first time I did it, I wasn't able to prove that point because the order actually did come out the same. So the thing that I want to draw your attention to is because it is a set, and we don't maintain any information about the order, although everything we put into the set is still there when we go through the fast enumeration in the loop on line 17, when we actually print it out, the order that we get out is different. And what is that order? Well, it's whatever order is convenient for the implementation to use. So it's probably an order that's based on the hash code of these different strings. And if we change the ordering around, we should see that the order ends up being the same because it's, is it the same? I didn't pay attention. The ordering is probably going to be the same, even though it's not the order that we put things in at. All right, so the first thing we see is that sets, like I promised, the ordering is not preserved. So the next question was, what happens if we add a duplicate? Well, again, sets are supposed to only keep track of unique elements. So what happens if we take Dr. Beebe and we try and add 2 of him, doubling the amount of presidents present at Westmont College? We cannot handle that many Beebes, and so we have used a set.
We have 2 Bs here. We have
2 administrative Beebes. Yeah, we have lots of Pattersons too. So what happened when we added that second Dr. Beebe? The set didn't change. We already had one in it, and so when we added another one, it just verified that it was there, and I don't know if it really overrode it or not, but it just didn't add anything because it didn't need to add anything. And so we could add lots of them, and the end result would be the same. We would still only have 3 unique elements in our set. Okay, so if that's a behavior you want, then you should choose a set. It's a design decision. All right, so what happens if we try and remove an element? Let's print out everything before we remove something. And then let's print out everything after we remove. So let's add another line here and say for Bagor. Wow. And after, take a look at that code, and now we run it. And if we look at our entire console, we can see that beforehand we had 3 unique elements in our set. We called the remove method. We called remove on an element that was in our set, and afterwards there were only 2 elements. Okay, it's a collection framework. That's the way it works. Pretty straightforward. Well, what about some corner cases? What happens if we remove an element that isn't present? All right, so well, that's a good question. Let's just try it out. Let's remove Dr. Adderson, a close but not related doctor that exists in someone's imagination. Okay, we're going to run this one, and we see that it was just had no effect. We were called remove, it didn't really do anything, and before we did the bad remove and after the bad remove, nothing in particular happened. So if we look at the documentation for remove by hovering over it, it says removes the specified element from this set if it is present, and more formally, returns true if this set contained the element. So that's something that we could, if we wanted to know whether or not it actually had an effect, we could actually say something like this. If removed, then we could print out a message that said Dr. Adderson was in the set. Because if Dr. Adderson was in the set, then names.remove would have, number 1, removed the element from the set, the side effect, and number 2, had a return value, whether something actually happened along the way. And so just so that we can see the effect, we'll go ahead and put an else statement in there, say Dr. Adderson was not in the set. And then if we run it, we can see the results of that call. Beforehand, Patterson C. Beebe, Dr. Adderson was not in the set, Patterson C. and Beebe. Notably, this doesn't crash. One of the methods in Python, one of the remove methods for sets in Python, would throw an exception if something wasn't present. So Java is a little bit more robust in that case. But if you actually want to know whether something is in a set, you have to do a little bit more work. All right, so that answers the question, how does add work? That answers the question about how does remove work. What about how do iterators work? Well, we kind of already did an iterator. So one of the iterators we know about the fast iterator. That worked okay. Could we do the index-based iteration? Is that something that would be possible? let's start it off and see how far we get. So far, so good. We're going to go through this loop one time for each element in our names set. That's okay because the set has a size. But what do we do now if we want to print out the element associated with index I? What should I put here? Any ideas? Well, I would have to be used somewhere. So this is one of the ways in which the list and the set differ. If this had been a list, we would have done this. Give me the ith element. But sets aren't ordered. So to say what is the first element or the third element in a set doesn't make any sense for the mental model of what a set is. And because of that, the set doesn't implement a getI method. There's no way to get a specific element in a set because a set's like a big bag of vegetables, I suppose. A big bag of whatever object you have. It's either there or not, and the ordering's not present. So we can't actually do an iteration over a set that's based on an index. All we can do is do one that's based on fast enumeration, or we can actually do one that's based on the iterator as well, because the iterator doesn't work with an index. So if I say iterator, so let's get the iterator for names, and then let's create a local variable for it. Oops, what did I do? There we go. Create an iterator over it, and we'll use our while loop construct. We can use an iterator that goes over it. So while iterator.hasNext, we'll say system.printout iterator.next. Okay, so that works. That works because a set is a collection, and a collection can be iterated over, but the order in which that happens isn't guaranteed. And so we see that of those 3 iterations that were possible in a list, only 2 are possible in a set because we don't have an index. Run that, make sure it runs cleanly. All right, so you see the set being printed out twice. You also see that the iterator and the fast enumeration end up producing the same output. That's because the fast enumeration under the hood uses the iterator as the mechanism for doing its iteration. Okay, so that answers some questions for us. How does add work? It works just like add does in a list, but if we add a duplicate, it doesn't have any effect. How does remove work? It removes elements, and if it's not present, it just moves on quietly. How do iterators work? Well, almost the same way, except that we can't index into the set. How does fast enumeration work? Exactly the same way. So let's take a moment and see how we might want to use sets for an application. And this is, I think this is a super neat application of sets. It's for spell checking. It's one that we did see in Python, but we do it a little bit differently in Java. And if we take a look at our code here in this project that I shared with you, you can see the spell check app, or the spell check, it's not an app, it's a spell check program here. And what I'll do is I'll walk through it with you, and we'll start with the main function. So in this main function, it's just a main function like the rest of them. It throws an exception, meaning it'll have an error possibly. And you can see in lines 44 and 45, we're creating 2 sets of strings. And in the definition in 44 and 45, because we're saying they are sets containing strings, we don't actually know whether the implementation is a hash set or a tree set. We know that calling the method readWords with one parameter, either dictionary or Alice30, is going to give us back a set that gets returned. But we don't know the implementation, and the way this code is structured, we're not supposed to worry about it because the features or the behavior that we want to work with are behaviors associated with a set, not with a specific kind of set. So we're going to call our readWords method. We're going to get some set of dictionary words. So I'll show you the readWord method in a second. But what it's going to do is it's going to open the file dictionary.txt, which is also in the project here, and contains a whole bunch of words like a dictionary would, of correctly spelled words, AOL. Got mail. And then Alice30, which is the text of Project Gutenberg's Alice in Wonderland, a copy of Alice in Wonderland. Alice was not a bit hurt, and she jumped to her feet in a moment. So what we're doing is we're going to create one set of dictionary words and one set of document words. Now this is a set, So we're losing all of the idea of sentence structure. When we read in Alice in Wonderland, we're just keeping track of the individual words. We're putting a word into a set, and so all the words that are in Alice in Wonderland will be in our set of words, but only one time. We're getting rid of all document structure. We don't care because all we're doing is a spell check. So the clever thing then happens on line 49. We're going to go through each one of the words in our document using fast enumeration. So in the body of the loop that starts at 49, we're going to look at each word one at a time in Alice in Wonderland. What order is it going to be in? We don't know. It's going to be we're going to see all the words, but we don't know what order it's going to be in. And we're only going to see each word once. And we're going to ask if our dictionary words set contains the word, then it's spelled right. And we're looking for misspelled words, so we're going to ask in line 50, if dictionary words does not contain the word we're looking for, then we have a misspelled word. And so in line 51, if it's misspelled, we'll print it out. And so in this really, really compact code, we're able to do a spell check for a document, given that we have a document in the dictionary available to us. So let's take a brief look at how read words works. This is a good example of taking a concept of reading words in from a file and abstracting it, because at this level in main, you could just believe that it does what it's supposed to do. But at some point, if you as an application programmer, but as a systems programmer, you might have to look at how it happens. So we're going to call read words with the file name we care about. We're going to create a set. This is ultimately what it's going to be returned down here. And you can see that the implementation is actually using a hash set. But that implementation information gets lost after we return it, because we return just a set. I mean, it's actually being implemented, but Java's only validating the methods associated with the set class. So we create this scanner, and what the scanner does is, we've only seen the scanner so far as a mechanism for reading input in from the user via the console. But here's an example of using the scanner with a different constructor so that we get input in from a file. So the way that we do that is we take our file name, we create a new file object, whatever that is. We don't know much about it, but we know that we can create a new one. And after we get that object back, we pass it into the scanner and create a new scanner. And so in this way, we have wrapped a file name with the file object, and we've wrapped the file object with a scanner. And now the scanner is going to be able to use that file in order to read in characters. So scanners have these methods, for example, one that says use delimiter. And what that is that's an expression that's called a regular expression. And what that's telling the scanner is that I want to break, my definition of words is anything that has the letters A through Z lowercase or A through Z uppercase in a sequence. And if it ever is not one of those things, then I end my word. So punctuation will break a word, space will break a word, numbers will break a word. And then we'll go through and we'll say, okay, we'll read in all the words from our scanner using in.hasNext while it has a next element. We'll get that next element, we'll convert it to lowercase, and then we'll drop it into our working set. Finally, we're going to end up closing this as long as we opened it cleanly, and then we'll return the result. Really nice abstraction, because we could read in a dictionary or we could read in Alice in Wonderland, and the work that gets done in this method is the same, regardless of what we're doing. But how we use those sets is different, and that's how we put it all together. So if we end up running this, you can see all the words that are found in Alice in Wonderland that didn't show up in our dictionary. So this might be a failure of our dictionary to have the appropriate words, or it might be something like a British spelling of a word in Alice in Wonderland. Uglification is not present. Northumbria is not present in our dictionary. This strange word right here is not present in our dictionary. I don't know if that's like an exclamation of terror or if that's some sort of weird punctuation thing going on. Merchantability, you can see clamor is a British spelling. That's like Alice hit her head falling down. Alice hit her head falling down and went. And XXX, I don't know what that is exactly, but I seem to remember from the Disney animation that there was like a bottle of alcohol falling down that had XXX on it. Maybe that's actually in the original text. Croqueting, pennyworth, etc. So we were able to do that because of the nature of sets. The way sets keep track of one particular word, and we did it pretty efficiently. We were able to do that really fast, and that's a kind of an interesting thing that we can do with a set as a result. Okay, now I would like you guys to take a moment and try something out. And what I would like you to do is I would like you to try typing in this code, or maybe, how should we do that? Maybe I'll type it in for us so we'll save time. And then what I want you to do is I want you to actually, let's walk through the code for starters, and then we'll move over to Eclipse, and then we can look at the effect. So for starters, this code shows on the top that we have a variable called names, which is a collection of strings. And that collection of strings is going to be implemented with one of 4 different kinds of collections. So the array list, the linked list, the hash set, or the tree set. And once we've done that, we are going to add these 6 names to our collection of names. And once we've added those names, we're going to ask what the size of the collection is, and then we're going to print out what's present in it based on the fast enumeration there. And what I want you to look at is I want you to see how choosing which implementation you end up using is going to change what ends up happening, even though the code is exactly the same. Okay? So to do this, let's cut over to Eclipse, and I think I already have this ready here. Let's see if I've got that. Yeah, great. And I'm going to drop it in examples live for you guys to work with. I'll get rid of the code that's present here. And I'm going to break our connection in a second so that we can each edit independently. Okay. Has everyone synchronized? Is that showing up on your version of examples live? All right. So just to reiterate, what I would like you to do is I would like you to try these 4 different implementations for names, run this program, examine the result, and make sure that it makes sense to you why you're getting the result that you're getting. Okay? So we'll take 10 minutes to do that. So we'll come back at 11:15, and if we need to take a stretch break or anything along the same lines, we can do that. All right, any questions before we do that? Okay. Oh, I was supposed to break the session, actually, because that's what I told her to do. Could have what I told her to do. Okay, back in 10 minutes. Okay, we're broadcasting again. We're just a couple minutes early. I'm just going to take a few minutes to capture the results so that we can talk about them. Ah! Oh, so loud. Wow, so loud. Okay, so we are back, and the question was, what do the different implementations of names cause our code to do differently? And so we saw we had an array list, a linked list, a hash set, and a tree set. And so we look at the output of those four different elements. We can see that, well, we kind of have two classes here that are slightly different. They're ordered left to right. I didn't label them, but it should be array list, linked list, hash set, tree set. So for starters, do you guys understand why the sizes are different?
Yes.
Can you summarize it for me?
Sets do not add things twice.
Sets do not add things twice. Great. You can also see that on the left, we have things that are twice. So the linked list, the list implementations on the left do have things that are twice. You also notice that on the left, the order is the same between array list and linked list. It is the order in which things were added, and that has been preserved. Lists are in fact, have an integrity to their ordering. So is there any difference between an array list and a linked list?
No.
According to this, no. And so what are we looking at? We're looking at the output of a couple methods. We're looking at the size method, and we're looking at the ordering. There's no difference in terms of those parameters. What's different would be the speed at which it took them to do this work. So the array list and the linked list may do them at different speeds, but the end result is the same because the data structure, the data model is the same. The way it does it is different. Now, with this small number of operations, we're not going to see that speed difference, but if we were to do this and multiply it times 1,000, we would see a difference in speed. So the two on the right, are HashSet and TreeSet the same? No. They preserved the same size, so they're following the set model, which is that you can only put things in one at a time. They're following the set model in the sense that the order in which you get them out is not guaranteed. It is not the same as what you put them in by, but the TreeSet is doing something different in the way that you get them out. What is it doing? TreeSet's on the far right. Well, bingo, right. TreeSet's alphabetical. All right, that's the natural ordering of the objects that are present, the strings. And so when we do the fast enumeration over the elements in a TreeSet, the order in which you get them back is not the order in which they went in. It's not random. It is the natural ordering of whatever object you're putting in there. So it uses the compare to method in order to figure out what the order is. So if it's strings, it's going to be lexicographic. If it's integers, it'll be numeric. If it's your type, if you decide to store your type in there, you're going to get them back in the order that you dictate by implementing the compare to method, -1, 0, 1. Right, so that's why you choose a TreeSet, is because when you do your iterator, you'd like to get things out in alphabetical order. The HashSet and TreeSet, just like the array list and the linked list, those are going to happen at different speeds as well. The HashSet generally is going to be faster. But again, at this scale, we're not going to see that difference. But while the array list and the linked list were only differed in speed, the HashSet and the TreeSet not only differ in speed, but in the output. So the TreeSet actually gives you something for being a little bit slower, right? It gives you ordering when you get it out. So again, if I were to give you this code and give you the output, you should be able to deduce from the output here what the implementation was that I chose for names. Now, you wouldn't be able to tell between array list and linked list, but you would be able to tell if I said list or set, HashSet or TreeSet. So being able to tease those apart is a good skill. Yeah, if I gave you the times, you could figure it out. You would have to, I would have to give you more elements though, because this is probably all going to happen in just a very small number of milliseconds. And what you're going to see is that the actual time to do the list operations is going to be small compared to just the time of getting the program started and making the function calls and such. But you could see that by adding things, because linked lists are faster at adding than array lists, you would see that the linked list would be a faster result because we're doing a lot of adds. So you could, if given the times, you should be able to tease it apart as well. Yeah. Or someone, an expert can tease it apart. Okay, so let's shift gears then. Excuse me. In our hierarchy, we had this one left side of our collection, one left side of our Java collections framework that included things that were descended from a collection, so things you add and remove and you iterate over. On the right side was this other small tree that was rooted in the interface map. And a map is a little bit different than a collection because it is a data structure that takes two different kinds of collections, a key set and a value collection, and there's an extraneous N on my slide, and it associates them with each other. So you use a map when you want to look up some data according to a key, but the data that you really care about is the value associated with it. So here's some examples. Maybe you wanted, a map is kind of like a small database. You can think of it like a little bit like a database. So let's say you wanted to have a database where you were able to look up people's names by social security number. So you might use a key, which would be a social security number, possibly represented as a string, and that would map to a name, in this case, Amanda. If we had other social security numbers in our database, in our map, we would map to other names. The left side are the keys, and the collection of all of the keys together forms a set. And so the left side has to be a set. It has to be unique. No social security numbers can be duplicated. You could also look up a major by name. So again, if you had someone, Amanda Smith, you could use that as the key, and you could look up a string, and the string might be a major, like data analytics. This would only work if you didn't have two people named Amanda Smith. If you had two people named Amanda Smith, you'd have to include middle names. And if you had two people with the exact same first, middle, and last name, you'd have to do something else, like use a unique identifier or some sort of ID. You'd have to choose which one gets to graduate, or they would both have to have the same major. So it's a difficult world when you have an exact same person, a clone on campus. Another one you could do is you could look up population by country. So if your keys are country names represented as strings, you could look up an integer. In this case, the population of Indonesia, 249,865,631 as of 2013, according to Siri. Okay, so what do we know about maps? Maps have to have unique keys. So the things that you're looking elements up by have to be unique. The keys are a set, and because we know that sets in Java can be implemented with a hash set or a tree set, maps also have the same options. There can be a hash map or a tree map. And whether it's a hash map or a tree map, it comes down to whether or not the keys are implemented as a hash table or as a binary search tree. And it has the same properties. That key set, if you implement it with a tree map, you can iterate over the keys in whatever the natural ordering is, like lexicographic ordering. So let's say we want to create a map. What does it look like to create a map? All right, so this is the code that we use to create a map. On the left side, you can see that we're creating a variable, and on the right side, we're reserving some space for it. So for starters, we have the type, and the type is map, and it could be map if we wanted to talk about things abstractly as just having the properties of a map, or we could use hash map or tree map because we're talking about specific implementations. But what we can't use is we can't use collection, because a map is not a child of a collection, because a map does something different than what collections do. A map kind of pairs two collections together. So we couldn't put collection there. The next two things are generics. We have to specify what the types are going to be of our keys and of our integers. And so we do that by placing the types following the map in the angle brackets there, separated by a comma. So the keys are strings, and the values in this case are integers. Then we get to pick the name of our variable. So this is our choice, populations. It's underlined in yellow there because when I screen captured this from Eclipse, I hadn't actually used populations anywhere. So it's giving me a warning. The name of the variable can be anything you want as long as it follows the rules of variable naming in Java. Everything from the equal sign to the left is enough to define a variable that will hold a reference to a map. On the right side of the equals, we're actually allocating memory for the map and pointing populations at that memory. So we use the new keyword to create a new object. Straightforward, same thing we do with anything. And then the particular implementation we're picking in this case is a hash map. In this particular definition, we could have used a tree map as well, because both tree maps and hash maps implement everything that a map requires. When we declare that we are going to create a hash map, we have to specify what the hash map is going to contain. We're indicating that it's going to contain strings and integers, and then these have to match. The string and integer decisions about what the hash map is going to contain on the right have to match what the variable on the left say it's going to contain. And then finally, we put the parentheses on the end, because on the right side, we're not defining a variable, we're calling a constructor. We're creating that space in memory and initializing it so that populations can reference it. So that's why we put the parentheses, because we are executing a constructor for that type. Any questions about that? Okay, so what we want to do now then is we want to see how do we go about using that hash map in order to create the relationships that we're interested in. So we do a couple different operations, and we use different words than we use when we create a collection. And we use different words because we want to emphasize the fact that we're not calling the same methods. So instead of adding an association, we say put, just so we don't confuse the fact that we're not adding something to a collection, we're putting a relationship in, even though in English they're kind of they're synonyms. So one question we might ask is, what if an association is already present? Well, if an association is already present, that's equivalent to saying, what if a key is already present in your key set? And just like if a key is already present in our key set, then if we put something in that's already there, then we're going to overwrite the existing key. But we're also going to overwrite the existing relationship as well. So if Amanda was a data analytics major, and we decide to put a new Amanda in, and this new Amanda is a computer science major, the relationship that's going to stick is the last one that we added. But Amanda's only going to be in our map one time in the key set. To retrieve an association, we ask, whose value do we want to retrieve? And so we would say, get Amanda. And a question we could ask is, what do we do if an association isn't present? And then finally, how do you remove an association? We use the remove keyword, just like in the collection, to remove an association as well. So let's look at these. Let me do an example of these, but we're not really going to be able to see the answer to those follow-on questions. What if an association is already present? And what if an association isn't present? We're not going to really be able to answer those until we're able to enumerate over the contents of the map. And since we don't have enumeration figured out yet, we're not going to be able to look at that quite yet, but we can start off by just creating it. All right, so kicking over to Eclipse, and let's try that again. We're probably okay not sharing for the time being. I'm going to create a new main method and store the code that we have here in a standby method. And get it out of our view so it doesn't confuse us. We're easily confused. Yes, standy. Right, so standy is what really, really brilliant computer scientists use when they mean standby. And occasionally make typos. Okay, so main, let's declare our type. Capital S for string, integer, and a variable name, we're going to call it population. And we're going to create a new specific implementation that maps strings to integers. And because we're calling the constructor, boom. And then we're going to need to import a particular implementation of map. Here again, we see that there are multiple classes called map that are in the Java library. Here's one in Java FX. That's not what we want. The generic Java collection framework is in java.utility or util. Great. Now we've got populations. Let's add one to add an association to our population. What if I were to accidentally use the keyword add? Wait, why isn't Eclipse helping me out? Why isn't it suggesting add? That's because add is not a method of a map. It's a method of a collection. And to help us remember that we're working with a map, we use put. And you can see that what put takes is a key and a value because we're going to put that relationship together and store it in our population. So we'll store Indonesia, and we'll store the population, I don't remember what it was, 249,863 and 192. I don't know if that's right, but I'm guessing. All right. So we put a relationship in between Indonesia and a population. Let's put one in. Favorite country, Tim? Russia. What's the population of Russia?
As of 2017, the population of Russia was 146,804,372.
Okay, remember that. 146,804,372. I forgot. 146,802. Well. Okay, great. My brain only remembers 3 things now. Okay, so now we have 2 relationships in our population database. And if we want to find out what's in it, we could say, all right, so now imagine we had hundreds and hundreds and hundreds of relationships in there, or one for each country in the world maybe. We could say the population of Russia is, and we could request population tell us what is the population associated with Russia. So this is the lookup. We stored a relationship here, and now we're looking up the relationship here. It's a lot like a database in that regard. So if we save it and then run it, you can see that the population of Russia is the integer that we stored previously, however, without the underscore commas that I put up there. Likewise, we could do the same thing with Indonesia. Get the result. And it probably should go without saying that getting a relationship doesn't change the structure at all. So we can call it several times, looking up the population of Indonesia. We're going to get the same result each time. But if at some point here we say populations dot remove, and we remove the reference for Indonesia, we're going to get a different result. At first, we get the population of Russia, and that comes back okay. Then we get the population of Indonesia, that comes back okay. But then we remove the relationship with Indonesia, and when we then ask to get the population associated with Indonesia, one of our questions is, what happens if you look up something that's not present in a map? Well, we just got our answer. What happens if you ask for a relationship that's not present? You get null back. So what you might want to do beforehand is you might want to check, and you might want to say if populations contains key Indonesia, then we'll go ahead and print it out. And we're not going to. It's not going to. So otherwise we'll say, I don't know about Indonesia. Okay, well, let's put Indonesia back in. Let's get the population of Indonesia. Print it out. And then, turns out we were wrong. We had the 2013 estimate. Indonesia's grown a little bit. So maybe it's now 279. And it turns out that, shockingly, Indonesia has exactly an even number of people. This, of course, isn't true, but this is helpful for us just to demonstrate what happens. But what I want to point out is that first we put a relationship in, two relationships in. We retrieve the relationship. So far, so good. We remove one of the relationships. We check to see whether it's present. If it is, we'll print out the population. If it isn't, we'll say we don't know about Indonesia. Then we're going to put the relationship back in. We're going to ask for the population. Then we're going to put the same key back in with a different relationship and ask what the population is going to be. Any predictions on what's going to happen on that last line? Yeah, it's going to replace the relationship that was previously present for Indonesia with the new one. But there will only be one value associated with Indonesia as the result. So the population of Russia is 146 million. The population of Indonesia is 239 million. We remove Indonesia. Suddenly we don't know about Indonesia. We add Indonesia back. The population is back in place. And then we overwrite Indonesia, and the new population is what it is. Okay? We can put many things in the value portion of this hash map. It doesn't have to be a single type. And we'll come back to that in a second.
Can you put a map as the value of the map?
Yes. So you can do the following. You can do something like, let's say that we would like to know all of the majors at a given college. And so we will say that this is going to be, the first string is going to be the college. And for each college, we're going to have a map that takes a name and maps it to a major. So we'll say, okay, great. Well, now the type on the right side is wrong here. Here we go. So now you have, we're using a data structure to look up by college, and what we get back is going to be a map that maps students to majors. So if we want to put something in here, we'll say national majors. We'll put Westmont College, and then what are we going to put in as a value? Well, it's not just a string. Now it's a map. So we need an entire map that maps students to majors. Could, but we need to create that map first. So we need a separate map here that is going to be the value. Okay, so now we have two maps. We're going to put into our national majors the map that we just made. And gotta get the name. And what do we do wrong?
What?
Are you complaining about the fact that you're a computer science major in my database?
Yeah, I think your database is inaccurate.
It's aspirational.
It's aspirational.
Yeah, it's our hopes and dreams for the future. So now we have a data structure that maps things to maps. Now this is actually what you're going to do for your homework assignment that's due for Chapter 15. For Chapter 15, you're going to have a map that's going to map a integer to a set of words. And what you're going to do is you're going to say, hey, let's look at the numeric keypad on a telephone. And you know how you can type in words using the numbers on the keypad? Like 2 is ABC and 3 is DEF. Well, it's great, but there are some words that map to the same number. And so what you're going to do is you're going to create a small database where you take a particular number, and that's going to map to a set of all the words that you could make from that particular sequence of numbers. So for example, if you put the number 2 as your key in the map, the list of values that are associated with it could be A, B, or C, because 2 maps to 3 different letters. I know, mind blown. We'll let you think about that a little bit. You have enough to do before that's due. Don't sweat about it too much. Okay, so that was a really great observation. You can use other things as the map. What about the key? Could I use a map for the key?
No.
Wrong. You can't. Yeah, you could use a map for the key too. It's a little bit more confusing to understand what that means exactly, though, because it means you're taking some kind of a map and all the elements that are in it, and that would have to be unique. All the elements in mapping would have to be unique, and then you're looking up some kind of value. So it's not that you can't do it. You can do it. It's just not clear what you're doing. You could, yeah, absolutely. Yeah, that'd be you know, the world's a crazy place. I've found myself doing some very, very complicated nesting of generics like this for just simple, not simple, but normal, not particularly exotic kinds of tasks. It's really powerful, actually. When you get your head around it, you can very quickly create some very powerful data structures just by using maps and lists in ways like this. Okay, so that's about the definition of a map. What if an association is already present? Will we rewrite it? What if an association isn't present when we get it? Will we get back null? How do you remove an association? You just call remove with the key you want to remove. What happens if you remove something that's not there? Well, it's probably the same thing as the set, but we could just sort of hover over here, and it says removes the mapping for a key from this map if it is present. So no problem if it's not present. The next thing that we often want to do is iterate over the values that are in our data collection. So for a map, we would like to look at the elements that are in the map. And so we have a couple different hooks into ways we can look at what's in our map. One is we can call the key set method, and the key set method is going to give us back a set that contains just the keys that are in our map. So kind of pulling that out from the associations and just enable us to look at the keys. And we can also pull out just the values, and that's going to come back as a collection because it's not unique. We could have Tim as a computer science major. We could have Lisa as a computer science major. We could have Boaz as a computer science major, in which case when we pull out the values, we're going to see computer science multiple times. But if we pull out the key set, we're only going to see each individual person one time. Usually what you want to do is you want to iterate over your map and you want to sort of print something out or do processing based on the key and the value together. So there are two options for how we can do this. The first one is we can iterate over the key set in any of the ways we know about iterating over a set and look up elements in the value. So let's do that first. So going back to our population database, let's comment at our top here. And
make a map, have keys that point to your own object that you're creating.
Yes, you can make keys that point to your own objects.
Instead of object person, and then in the person object, you can name, face, type, weight, height, all that.
Yep, like an electronic medical record.
Yes.
Sure. In order for map to work, the class that you use as a key or the class that you use as the value have to implement some particular methods, though. So if you want to use your class as a key in a hash map, it has to implement the hash code method. And that's something that Eclipse will generate automatically for you if you ask it to. And if you want to use it in a tree map, you have to implement the compare to method so that it knows how to put it in order.
Would it make sense to implement all of those methods safely, like if someone wanted to?
Depends the context in which you're planning on using your class. So because it takes work, typically you don't implement it unless you need to. But if you find yourself, so usually when I'm designing something like this, I don't implement it, and then I'll find myself some point later in the design or in the implementation of the design needing to use a tree map, and then all of a sudden I can't use my class because I didn't implement a compare to, and so then I just go back and I implement the compare to when I need it. Yeah. Okay, so let's add one more country. Boaz, favorite country? Thailand. Hey, what's the population of Thailand, Siri?
Okay, I found this on the web for what's the population.
Sorry, I have to be more formal. You have to use my angry robot voice. What's the population of Thailand?
As of 2017, the population of Thailand was 66,188,503.
All right, ready? Help me out. 550. Okay. I've been to Thailand several times. It's beautiful. Except for what? The sky's not beautiful? Wrong color. It would be beautiful, just unexpected. Okay, first thing, we want to go through and we want to iterate over this data structure. So we're going to pull out the key set. So populations.keyset is going to return a set. So we'll just call it keys. So now keys is a set. We know how to iterate over a set. We can do it with fast enumeration. We can do it with an iterator. We can't do it with an index because that's something you can only do with a list. So what we'll do is we'll just say, okay, for string k in keys, let's look up populations.get k. And we'll store whatever the population is as we go through it. So then we can say, all right, well, the population of, well, this is an iterator now. So we don't know exactly what country we're going to be working with in the context of this loop. So we'll use a variable to stand in instead. We know our country is going to be our key, and then the population itself is going to be p. So we pull out the key set, we iterate over the key set, we get the particular key in that iteration, and we print it out. And when we get the result, we see something very similar to what happened when we worked with our set. When we were enumerating over our set, we saw that the order wasn't respected. The order in which we put things in, Indonesia, Russia, Thailand, is not the order that we got them out. Thailand, Indonesia, Russia. That's because we're implementing it with a hash set. The hash map has a hash set for its keys. So what do you suspect is going to happen if I choose the implementation TreeMap instead of HashMap? Will be ordered according to the natural ordering of whatever your keys are. So strings are ordered lexicographically. So we output Indonesia, Russia, Thailand. It's alphabetic. Now notice it's not in order of the values. It's in order of the keys. Right? We're not going by increasing population order. If you wanted to do something in increasing population order, that becomes much more tricky. Okay, so that's one way. That's option one of doing an enumeration. The second option is to iterate over the entries directly, and this is a little bit like an extension of the fast enumeration specifically for maps. And the way we do this is we ask for populations not to give us the key set, but there's another set that we can get called the entry set. And the entry set gives us things back in pairs. So each time we go through this loop, we have this variable e, and it's this type entry, which we haven't introduced, but it's easy enough to use. We'll say e.getKey and e.getValue. So it's like a tuple in Python. The entry set, you just get things in pairs, and that variable e is the pair. You can get the key and get the value. And so if we run that, and we can comment out this code so we don't confuse ourselves, we'll see we get the same result. It's still alphabetic because we're still using a tree map. And if we go back and we change our hash back to a hash map, oh, sorry, I gotta import it. Once it's imported, now we go back to an arbitrary order: Thailand, Indonesia, Russia. Whether we do it with the key set iteration or whether we do it with the entry set iteration, either one of those is going to conform to the right ordering that we expect with HashMap or TreeMap. Okay. Why can't we look up elements of a map using an index? Boaz. That's right. There's nothing about a map that has any kind of ordering associated with it. There's associations, but those keys are in an arbitrary order. So we can look up what Indonesia's population is, but we can't look up what the third element in the map is because there's no sense in which there is a third element of a map. In some world, you could imagine a kind of map where there is an ordering, but that's not the contract of what a map does for us now. A map is a set paired with a collection along the way. Maybe just as one last example, let's look at iterating over the values, see how that works. So we could, for example, instead of getting the key set back, we could get the values back. This is a collection. Let's change the type. This is a collection. What's going on? Oh, right, because it's the keys, it's not strings, it's integers. And then if we do a fast enumeration over the collection, it's not possible to go backwards. So a map is a one-way mapping from keys to values. You can't do the reverse. You can't look up the key associated with the value. Well, I don't think you can. That you didn't used to be able to. That may be something that got added in a recent version of Java. I don't see anything like that. Some languages actually enable you to do that, and it gives you back a list of all the keys that have that value. And in this, I don't think Java's added that yet. So the best we can do is say there is a country with a population of I. Now if we run that, we'll get the collection of all the populations, but we don't know anything about the key that generated it because we asked for the collection back without the associations present. Does that make sense?
Yeah, so there would be no way to order them
You could order them by increasing population size. Once you have that collection, you could do the following. You could say collections collections.sort. So that's going to, what did I do wrong? Stand by while I figure out what is going on. Oh, yeah, fair enough. Okay. A collection isn't ordered necessarily. Only a list is ordered. So before we could sort it, we would have to create a new list of integers. that would normally implement all those things. All right, so we have values coming back. Because there's no ordering in a collection, there's only ordering in a list. We have to create a list. This has nothing in it, so instead I'm going to put all the elements in our collection in it. Now I'm going to actually sort them. And then I'm going to iterate over the sorted list instead. So that'll sort things, sort your list of populations from lowest to highest, if that's what you wanted. But actually getting the country that's associated with that population is much trickier. You would have to, for every time, everything you looked at in that sorted value, you'd have to search your entire map to find something that matched it. It's a little tricky. Okay. All right, so that's kind of a summary of the maps. Really useful. It's hard to really get your head around it until you start using it in practice. But between lists and array lists and map, you get a lot of power in your data structures. Before we're done for today, though, there's a few other ones that we need to touch base on, and I want to just fill those out. One that we still haven't covered is a stack, and a stack is a list that has two extra methods on it. It has a method called push and pop, and the idea with push and pop is that you're going to treat this stack, if you only use push and pop, it becomes like a stack. And what that means is you have some list, and what push does is it pushes something onto one end of the list, and when you have pop, it takes it off that same end. And so you could actually kind of think of it vertically as being a stack of pancakes or something that's in a stack. You push something onto the top, and you pop it off the top in order to get it out. And so like we talked about with a storage unit or dropping something down a well or something where you can only take things out after you've taken the things out on top, it gives you a different kind of data structure to work with if you want. Now, stack also happens to implement all the things that list implements. And so it may not be entirely obvious why you would want a stack, but there are some operations that lend themselves well to using a stack. So for example, one of them would be the undo function of a word processor. If you think about the kind of things that you might do in a word processor, and here's a little bit of code that sort of demonstrates that. It's a toy example, but it points out the idea. Let's imagine you had a bunch of actions, and you kept track of that in a stack, and you would push things onto the stack. So first, you edited the title. Then, you changed the font. Then, you deleted a word. Then, you typed a word. Well, if you wanted to undo those actions, you'd undo them in the reverse order in which you originally did them. So when you would pop something off that stack, and if you were to undo your last action, well, the first thing you would undo would be to type a word. So you'd untype the word, then you throw it away. Well, if you undid again, you'd undelete that word and throw it away. If you popped again, you'd undo change that font, and then you would undo edit the title. And you can see that you have to undo in the reverse order in which you did the actions because they affect each other as you go along. And then you can redo them by putting them back on, right? Or control, what does control Y do? Like, just,
It undoes control Z.
so it's redo.
So redo.
Yeah. So what would you have to do to actually have that? You'd need two stacks, right? So you have the actions that you did. You undo, you put it over here. You undo, you put it on that stack. You undo, you put it on that stack. And then if you want to redo, you take it off this stack, you put it back on the old stack. And then as soon as you do something new, you kill this entire stack because you can't, as soon as you do something new, you can't redo anymore. It's horrible. Yeah. So that's a good example of a place where you might actually want something like a stack data structure. What's another one? Well, this is a little bit more complex, but if you think about the function stack in Java, that's a stack as well. And what I mean by that? Well, every time you call a method, you pause, you create all the local variables associated with that method, and you run some code. But if you call another method within that method, you put that method on a stack. And if you go deeper, you call a method in that method, you go deeper, and you go deeper, and you go deeper. And eventually, when you return from a method, you pop the last method off, and you replace it with whatever the return value is. Then you pop the last method off. So the first one is going to be main, and maybe for our Alice in Wonderland example, then you call read words. And then when you're done with read words, you take rewords off the stack, and you go back to main. But what if rewords called another method inside? You would have main, and then rewords, and then maybe create a new scanner. When you're done creating the new scanner, you pop it off the stack. When you're done with rewords, you pop it off the stack. So this idea of having a stack of function calls, technically frames of data, is central to the way in which modern computers abstract the process of function calls. And if you're familiar with the website Stack Overflow, the word stack in the website Stack Overflow comes from this data structure, and in particular, the usage of this data structure in order to capture multiple calls to a function. Overflow means you've put so many things onto the stack that you run out of memory, and the next thing that you put on the stack overflows. It's a problem with recursion. Okay, so that's a stack. Another kind of data structure that we might want to use is a queue, and a queue is different than both a list and a set. The idea behind a queue is that you just put something in on the back of the queue and you pull something off on the front of a queue. So you think about it in terms of, usually you think about it in terms of a line at a teller, maybe a bank line or a line at a fast food restaurant, something like that. It's a little bit more abstract than that, because just because you put something in one end doesn't mean it has to be the first thing that comes out. So the basic idea, of course, is to just put things in an order. So let's think about a print queue. If you have a printer at a library and there are a lot of people that are printing, you print something and your computer puts that paper onto a print queue. And the things that the printer looks at that queue and says, okay, what's the next thing I'm going to print? Well, it's the first thing that was printed. So first in, first out, or FIFO is an acronym we use to describe that. Kind of makes sense. That seems fair, right? That's sort of the normal expectation of the way a line works. But as an abstraction for a queue, you just have things go in one side and come out the other side. How you represent them inside, what the implementation is of how you keep track of those things, can vary. A natural way to keep track of it, though, of course, would be a list. But a queue doesn't require you to keep track of a list. A queue just requires in one end, out another end. How it gets through there is not specified. And because of that, you can have a basic queue implemented with a linked list. So here's an example of using the queue interface, but implementing it with a linked list on the upper right. You can see that we add things to the queue with just the add method, and then we remove things from our queue with the remove method. Now this might not seem so different, right? This is kind of what we did already with our linked list, but it has an in, it has an out. If A was papers that you were printing and B was a paper that you were printing, you would print things out in the order that they went in. A, B, C go in, A, B, C come out. But a priority queue leverages the flexibility in the queue representation to allow each thing to have a particular urgency. So if you create a priority queue, you still put things in, but the order that they come out in isn't necessarily the order that they went in. Instead, they come out in priority order. So very much not first in, first out. What is the priority? Well, the priority is determined by the compare to method. So unless you make your own class, it's going to be the natural ordering for a particular element. So for example, if you put a bunch of strings into a priority queue by doing add, when you remove them, they're going to come out in alphabetic order, because that's the natural ordering. The priority is the natural ordering. So as a last exercise, well, that compare to has to be implemented. So you have to define what does a color mean to have a priority. So maybe it's closer to white, or maybe it's closer to black, or maybe it's redder, whatever you want to do. Yeah, you could do something like that. So let's try and make one. Do you want to try and implement that?
Do we have something else to learn today?
This is the last thing to learn.
Oh, okay. Let's do it.
Okay. All right, so for what we want to do is we want to have a priority queue. So let me, again, rename this. Oops. By. All right, and so what we want to demonstrate is we want to demonstrate how we use a priority queue. So we're going to create a priority queue called queue. That's going to be a new priority queue. This is not going to compile because I haven't given it a type, but we're going to start with this. All right. And you said color was a good thing. Do we want to stick to that? Another thing we could do is like to-do lists. That's sort of a natural thing as well. Okay. So let's create a new class, which is going to be our to-do list. We'll put this next door. And usually when you think about this sort of an application, you think a to-do list has a priority, right? So how do we want to define what a priority is? Should it be an integer? Should it be a letter? Should it be?
Yeah, let's call it an integer. Or actually, let's make it a string of exclamation marks.
Okay, how many more exclamation marks, the more urgent it is? Okay.
The max would be 3.
All right, so any particular to-do is going to consist of an urgency and a name. Good? All right, and those will be private. And we need a constructor, so I'm going to use the Eclipse feature of creating a constructor. So boom, there's my constructor. So that'll enable us to create it. And then we're going to need to implement a compare to method. We don't get that for free from Eclipse, unfortunately. So first of all, we're going to say that it implements comparable. This is going to help us out here. If I type it right. Comparable to. All right, so here's our compare to method. So we have to compare this versus the one that's coming in. And if this should come first, it's got to have we've got to return a negative number. But if O should come first, we've got to return a positive number. So we'll just compare. We'll say my urgency equals urgency dot length. Right? And your urgency is going to be the length of O's urgency. We need to access. So O is the object, urgency is the instance variable. We can't get to that because it's private, and so we need to implement some getters for this. So we'll go over here and generate getters and setters for name and urgency, make them public. Okay. So now we have get urgency, get name, and set name. So down here in our compare to, let's give us a little more screen space, say all right, and then we'll just say if my urgency is greater than your urgency, typo, then we will return -1. If my urgency equals your urgency, then we will return, wow, can't type, end of the lecture. We'll return 0. And lastly, if my urgency is, if my urgency is less than, then we do that. My urgency is greater, then we return positive. Okay, and we have some error. What's my error? Add a return statement. Return here, return here. Oh, right. So if we're not less than and we're not equals, then we must be greater than, so we're just going to return -1. Return 1 no matter what. Okay, so now we have a to-do class, and we have a compare to. So let's go back. Let's go over here and use it. What's in our priority queue? Well, to-dos. And we're going to instantiate it with to-dos. And spell it right. Now let's put some in. Let's say queue.add. What's our first to-do? How urgent is it?
Very urgent.
How many?
Let's say 3.
3. Critical. Funny you both said that at the same time. All right, now I'm looking at my constructor and I see that we got them backwards. Urgency comes first, so let's fix that. Okay, let's add another one. What's next? Homework. Okay, for this class? and eat lunch.
That would be a 1.
All right. So now, while q dot is empty is not true. So while the queue is not empty, let's print out our order of urgency. And we'll say q dot remove. And we better kind of describe what we're doing here. Here are your priorities.
So you can remove something and print it through a screen at the same time.
Yeah, so the remove method has a side effect, which is it takes something off the queue, and it has a return value, which is the thing that you just removed. Retrieves and removes the head of the queue. All right, so now if we run this, what are we running? We're running examples live. Oh, we didn't. We need. So we ended up printing out these references. That's not helpful. In order for this to look right, we have to implement a toString method. So let's just implement toString real quick. We have to return a representation of this object as a string, and so that can just be return this.name plus colon this.urgency. Great. All right, now run it again. Right, there you go. Here are your priorities. We got the ordering backwards. So if my urgency, oh no, I had it right the first time. If urgency is high, it has more. If urgency has more question marks or exclamation marks, then it should come first. There we go. So now here are your priorities. Do your homework, do your laundry, eat lunch. If we come back here and we decide to add some more priorities, eat dinner. We better say eating lunch is a little more important since that's sooner. Let's add one more. What's something really important that we're adding at the end? Besides using the toilet. Thank you for that one. Showering. Wow, it's like Maslow's hierarchy of needs in here. Somewhere in there, self-actualization. All right, so there are your priorities. You better do your homework first, your showering, then your laundry, then eat lunch, then eat dinner. And the way what's happening is we're leveraging the queue's behavior. You put something into the queue, but the way it comes out, we're leveraging the priority queue behavior, but the way it comes out is based on priorities. And in order to get a priority we cared about, we had to implement a compare to method in the class that we wanted to implement it in. It didn't come random. Oh, when it's equal? Yeah, when it's equal, the ordering is not defined. Yeah, that's a good question. Okay, great. So, summary, what did we do today? Well, we finished up looking at the Java collections framework. It's one thing to look at them and to have the ability to manipulate them. That's important. But understanding what the right thing is to use in any given particular problem that you have is much more of a challenge. That's the skill of knowing this information. It's one thing to know it. That would be kind of the techne element of this stuff. But how to use it is more the episteme kind of level stuff. How do you synthesize it? How do you choose what's appropriate? That's when you start becoming the difference between a programmer and a good programmer and an expert programmer is knowing how to assemble these things into data structures that map the information that you're trying to keep track of. So we've looked at collection and all the children of collection, including list, queue, sets, and the implementations that you can choose: array list, stack, linked list, priority queue, hash set, tree set. We also looked at map and the two implementations for HashMap and TreeMap. And we looked across the board why you might choose one over the other, both in terms of speed, the mental model for what it represents, and then what you can actually accomplish with it. Any final questions before we wrap up? Anything online, folks out there? Great. Then that is it for today. We've got a lot of work to do. Unfortunately, that means class is over. Boo! And we will see you tomorrow.